So this session, another drawing detail session, and this is on the Leutschenbach school in Zurich by Christian Kerez. Anybody? These are all. This will all be on mole, by the way. So you don't need to write. No, I mean I'll put the PDF up as well, so you don't need to watch me again, obviously. Okay, so I think it's a really interesting project, and it kind of follows on from last week where we were talking about kind of structural specificity, structural tectonics, and again, this is another project where structures are probably the main design driver for the project. Now, Christian Kerez architects are very interested in structure. This is the kind of study model that they produced for this building, which I find really intriguing, that from an early stage they are playing with different structural possibilities. So they don't see structure as something that you need to make the building stand up. It's the kind of first thing they consider for a lot of their projects. And what you can see with this school is they decided quite early on this configuration of floor slabs. So we go from sort of thin to the sort of widely spaced slabs here, and then they started playing with the different structures. These are some of their study models that they made. So if you look at the ones along the back, they're all about structure. So all they've got is slab and structure. There's no stairs, there's no glass, there's no materials. That's purely what they're exploring at that point. And this is the kind of large-scale structural model that they make, which I think is really fantastic, actually. This is I think it's about this big, and as you can probably see, it's made from sections of softwood, probably with some, I'm not sure, maybe there's some plywood in there, or just planks of softwood. But the thing is, because they make them of a certain size, it means that they can fix them together properly. It's not like fixing together little fiddly bits of balsa wood, where if you try and fix it, it breaks. If somebody sneezes close to it, it'll fall apart. These, you could probably sit on this and it would be fine. And something I'm pushing with my students at the minute is to, if you're going to make a structural model, why make it out of little tiny fiddly bits? If you make it out of something a bit more substantial, it's not going to cost you any more really in terms of wood, but you can drill it and you can screw it and nail it, and it's just a bit more robust. So this is the kind of model that they were making, and this is the building. Anybody seen this building before? No? Okay. So it's in Zurich, or it's sort of in one of the outskirts of Zurich, and I visited it. These pictures are taken in January. Okay, so it was a bit of a dreary day, and I visited the school, I think it was 2 years after it was finished. I'm not sure exactly when, around about 2009 I think I visited it. And what you might notice in my pictures is it was a weekend, so the school is empty. Okay, I'm afraid the pictures I've got, you've either got my pictures, which are just a sort of dreary Saturday, or you've got the professional photographer's pictures. Well, of course, they wouldn't let any people in those pictures. So it's a bit of a shame, because when I was there, you could see all the furniture was in, and the building looked really really well loved, really inhabited. But the pictures don't really capture that inhabitation. So I'm afraid the pictures are a bit more, they make it look like an art gallery, which is not what it's about. So, let me just go back. What you notice, if we just look at the elevation, we've got 1, 2, 3, 4, 5 floors. So it's a multi-story school, and there aren't many multi-story schools around. BDP did a very successful multi-story school in London on a very tight site, and in the BDP scheme they actually built playgrounds up at higher levels. Now, the idea here was, because they had a very restricted site, they would build the school high to try and save some landscape, save some playing fields. Now, you might notice, having saved that landscape, they haven't exactly done a lot with it. And it's still like that. It's just sort of grass, which, I don't know. I think that's a real disappointment, to spend all that money on a high-rise building to save the landscape and then just to put grass on it. So, anyway. But, they did achieve that. If they built this as a conventional one-story, two-story school, it would have virtually filled the site. So, I think they have achieved something with that. Now, what you might see immediately from this view as well is the building is asking us to engage with its structure. And we see here we've got this 3-story high structural element which zigzags across the facade. And then we've got nothing. And then we go up again and we've got this another very high structural, very strong element on the facade. And then we come down to the ground, and again we have nothing. So the building sits on glass. Well, that's how it kind of reads. And the building, it plays these kind of games with the viewer, where the structure is foreground, then the structure is background. The structure is on the facade, the structure is internal. And, I think it's kind of really intriguing structural tectonics that they've created in this project. Let's just have a quick look at it. Some of my images, for some reason I thought it was good to tilt the camera. Not sure why. But that's the sort of view. You've got these balconies. Okay, concrete balconies. This is actually a steel frame in here, a steel truss in here. And the detail that we're going to draw a little bit later on is one of these balcony junctions. But if you just notice here, the key thing to notice is that the balcony is all flush. So the soffit flush, steelwork flush, glass flush. There's no sort of frame sticking down there. That was clearly the intention. That's the view looking the other way. And it also, on 2 of the floors, got this very interesting soffit, where the soffit is profiled, which is sort of, well, it's probably helping with the cantilever, but it's also sort of expressing that there is a structural element there. Okay. It's got this amazing staircase on the outside. I say it's amazing because you look at the cantilevered balcony, and then they've cantilevered a stair off it, and there's no support here. So there's no structure coming down under that stair. Now, what they must have done, presumably, is that this depth of the balcony presumably is a bit oversized throughout, so that when the stair joins it, there's no thickening of the structure there. And they obviously wanted that kind of purity. That's the corner. So you see expressed structure here, and then we come down, and the building would appear to be sat on glass. Okay. That's the profile soffit, in situ concrete. And you see the way that it interfaces with the glass is the glass just sort of disappears into that concrete. And presumably, for the sort of this expression that they were aiming for of the building sort of sitting on glass, they didn't want to destroy that by having window frames at that junction, so it's kind of frameless. Even the vertical joints here between the glass is it's a frameless system, so there's no cap on that. That's the view of the soffit again, close up. I mean, you can just sort of make out that they had inhabited the building. There's lots of colourful furniture in there, lots of children's toys, and I kind of think the idea is probably that the sort of very grey, austere building provides a background for the inhabitation. Pictures don't really capture that. That's the view on the corner. That's the view on that side. And at night time you get this amazing effect with when the lights are on. Okay, some more images. This is a structural model which I think is really helpful. It explains the way the structure works. It's quite a complex structure, to be honest. So this is the ground floor. We've got these really, really strong, kind of oddly shaped columns, but they're basically columns, and there are 6 of them. And then sat on that is this enormous truss, 3-story high truss, which, as you can see, is achieving this huge cantilever on the corner. Then, bearing in mind that the next floor is another floor of glass. So when we were looking at the elevations, the next floor has no visible structure. Now, to achieve that, they then have this transverse truss, which is spanning the other way, which stops short of the glass, so you don't see it. And then sat on top of that transverse truss is another full story height truss box around the edge of the building. The top floor is the gymnasium, so that's partly why it's got this extra height to it. So that that shows you the sort of the complexity of the structure involved to achieve these kind of tectonic effects. Now you could argue, you could say, well, that's a lot of steel. Because you're playing these structural games, you have to put a lot more tons of steel into your building, and that would be a valid criticism of the building, that in terms of embodied energy, you're putting in all this steel. You'd have to make a judgment on whether that's worth it or not. That's just a different view of it. But you see the sort of incredible cantilever effect that they achieve at ground floor by having this 3-story high truss. So ground floor plan, that's those big columns, those three-legged columns, and then no structure anywhere else. So, fantastic in terms of open plan use, flexibility, no columns, nothing at all. And that's the 3rd floor plan, and these red lines, these are my red lines, showing you where those trusses lie. So this is the 3-story high truss. These here are a sectioning through the truss, and the design is such that you can fit doorways through that truss. You can walk through that truss to get into the classrooms. But again, completely open plan all the way across like this, completely structure-free, column-free. So in terms of partitioning off these classrooms, fantastic for flexibility. And then the 4th floor, which is the gymnasium. I make it 5th floor. I'm not sure why they count it as 4th, but anyway. The top floor has this enormous truss around the edge and nothing inside. No structure inside. And that's the section. That's the short section. Those big columns, 3-story high truss, the transverse truss, and then the gymnasium floor. And you might notice that the gymnasium has a truss over the top of it. The roof is not actually flat. It's got some air handling units on the top, but because of the height of this building, you never actually see that shape. You'd have to be, I don't know, 4 or 5 kilometers away, I guess. You'd have to be quite far away to see it. So I thought that was quite clever as well, that they've used this truss up here to help out structurally, and it doesn't actually matter that you have a slight slope on it. That's the end elevation. So we've got this profiled soffit. On the 4th floor, it's on this direction, and on the ground floor, it's on the other direction. That's the the image. These are the sort of more technical drawings. This is a view, ground floor inside, looking at the glass to the outside world, and those enormous columns, and the profiled soffit. So all of this above your head is cantilevered from here. That's on one of the upper floor lift lobbies with this internal truss, and again the profiled soffit. That's the stair. This is a glass plank, so it's like a reglet, like on the railway station, the railway depot last week. It's a glass plank. You know, really good product because it's structural, or rather, it's quite robust. You get some sound performance from it. Lets light through, but it's not completely transparent. Yeah, good product. You get a fire performance off it. So just some more views. I mean, these are the professional photographer views, and you know, this is what I mean by it looks like an art gallery. Yeah, I think you've got to imagine it full of children and children's toys. You know, it looks a lot more lively than this. You know, it doesn't look like that anymore. That's the long section. It does have a basement, and these big steel columns I think they just sit on huge blocks of concrete. And that's the truss above the gym, up there. And that's the section through all of these balcony edges, and we are going to look at one of these now. Okay, so we're going to draw this detail. That's a view in the gymnasium. Any questions or comments on the building before we start to look at that detail? Don't know. I don't know. Probably. I don't know. I mean, they obviously have more money in Switzerland for schools than we have in the UK. I don't know. I'm sure it was quite an expensive school to build. Yeah. Yeah. But, you know, having said that, in terms of longevity, it's very high quality, very robust. I don't imagine anything failing on this building. It's not going to get damaged. You know, the criticism of the current schools program in the UK is that we're building schools that will only last 20 years. And we're building them on the cheap, we're saving money, but in the long run you don't save money if you have to knock them down and rebuild them. So I don't actually. Yeah, I don't know, I'm afraid. I mean, it's very common in Switzerland to have basements for bikes and storage, so...
Yeah, we have problems in the outside when inside the building heating, and you look into cold.
Yeah.
Are all the facades the same?
Yeah.
Is there any sort of...
Yeah.
Nothing to sort of mitigate overheating?
Well, yeah, I mean, it's a good point. There is the overhanging balcony, but yeah, it's another potential criticism of this school, that it is mechanically ventilated. There's no natural ventilation, and yes, north, south, east, west, all the same. Clearly, they're not getting the same sun or wind. Yeah, I think there's a sort of triumph of aesthetics over performance, perhaps. I mean, it'd be interesting to know, you know, whether they've done a lot of simulation of that overhang and whether it's actually shading very well. Possibly. Okay, so let's go into the drawing. Right. So we're going to draw the condition where that balcony meets the main building. Right. So, as usual, I'm going to draw at 1 to 5. Okay. So. So I'm going to start by drawing the main structural slab in the building. All right. So generally I like to start by drawing structure, something kind of fixed. So reinforced concrete slab. Okay. And the key thing on this detail is what they're trying to achieve is we're trying to join a balcony on here, and we're trying to glaze it top and bottom, and we want that junction to be incredibly clean and flush. So we don't want to see any sort of mess here, any frames, and that's the kind of the real challenge here. There's also a concern about cold bridging, because we're going from inside to outside. So let's have a look at that. Now, the solution that they actually adopted here is, in order to structurally fix the balcony, what they've done is actually embedded steel work into the concrete. Okay. So I just draw this. Now, if you're doing a balcony, if the structural conditions permit it, you can just use a thermal structural connection. So the company to look up is a company called Shoke, and they produce. You can't read that. I'm not going to. I'll go. I think I've got an extra letter in there. Anyway, if you Google something like that, thermal connections, it will work. Okay. Now, what they produce. Let's draw one. For more structurally more simple connections, what they produce is an insulated connector, which basically has a whole load of very clever sort of plastics in it, and they produce steel to steel connectors, concrete to steel, concrete to concrete, and basically all you need to be aware is that it's a product. It's got a whole box of tricks inside it, but it allows you to fix steel plate. So if that was two steel beams, for example, you can connect those together, and it won't allow a lot of heat penetration through the connection. And it's structural, so it will perform structurally. So fantastic product for a lot of sort of balcony conditions. But in this instance, I think that just would not have been strong enough. Okay. So what they have done instead is they have cast into the concrete projecting steel work, which is something like this. Now, you may think it's slightly odd to be having a concrete slab which has steel work embedded in it, but it's actually not uncommon. Jessup West over there has got loads of steel work in it. Basically, Arup's committed to, I think they committed to a 250mm thick slab on that building in concrete, and the only way they could achieve it is to have a huge amount of steel work in there, to the point where the engineer described it to me as concrete reinforced steel. Basically, it's just a steel frame with a bit of concrete poured over the top. Well, because that's what the architects wanted, and because it gives you thermal mass, gives you the soffit, it gives you fire protection. Concrete finish is great to work with. Steel work, you have to fire protect it, you've got all the junctions. you know, steelwork's pretty messy actually. Yeah.
But then why did they not just have a thicker slab?
Because London
Yeah.
won the job,
Yeah.
and they promised a 250 mil slab. This is what
Was that reason?
yeah, this is what I've been told. So Arabs committed to it, but then for Arabs it became a, you know, Arabs are interesting engineers. You know, it became a challenge. They wanted to do it. I mean, yeah, who's going to know
Yeah.
if it's that?
But if it's like a bit like stories and you change it 100 mil for each story, then
Yeah, a little bit. Yeah. Yeah. Okay. So imagine what they've got here is they've put into the concrete steelwork, and that steel beam at a certain point is projecting out of the concrete edge. And we're going to talk we'll talk about thermal bridging at some point. Now, what they've then done, try and draw this right, is something like this. They've cast onto that they've cast it in situ the balcony. And they've cast the top of it with a slight fall on it, which is to take the rainwater away. So it's not a precast balcony. It's cast in situ, which I guess allows them to achieve that sort of monolithic appearance where it's kind of continuous. So they've cast that at some point. Okay, and what you'll see is that they're leaving these gaps are left for good reason. Then the structural frame, it does vary from level to level, but that kind of sits in here, and on this level it's a channel, but on other levels it's a box section. Okay, and the underside of the concrete here is exposed. That's the exposed soffit, and in some cases it's the profiled. And then what have we got? Here we've got. Try and draw this right. The glazing sits in here, and it's triple glazed. Okay. And that is held in place. I mean, this would be a system, so it's not like you would be designing it as the architect. And that has probably an aluminium backing box and these sort of aluminium shims which hold it in place. I think I've probably not quite drawn it right, but I believe it is designed so that you can take that sheet of glass out. So by kind of removing these blocks here and at the bottom, you could take that glass out to reglaze it, because obviously you can't be taking the balcony off to fix your glass. Okay. So, and crucially, it's flush. So there's no frame, no glazing frame. Then what we've got in here is a roller blind. Something like this, which then on some steel wires brings a roller blind, like one of these, on the outside, presumably electronically controlled, I'm not really sure. Okay, and then there is, looks like there's a little flashing in here, just an aluminium flashing here, and looks like there's a little aluminium flashing in there. Oh, and there's a little cover plate on there. Zoom in a bit on that. So although this underside of the soffit, although it's made up of lots of different bits, it's flush, and these little gaps here, all they register to the eye is little tiny shadows, little tiny shadow gaps. But the overall effect is smooth flush. Okay, so that's the underside done. That was pretty simple. Now for the top, let me get this right. We've got the glaze. In fact, I'm going to start with the slabs. Let's get this right here. So what we've got here is paving slabs, which are probably concrete paving slabs. So the top of the balcony is the paving slabs. And what they've done here actually is they've simply applied a liquid waterproofing to the top of the concrete, which, as I said earlier, is on this angle. It's on this fall to shed the rain. Now, I guess because you've got this big overhang, you're not really, you're very unlikely to actually get any water in there anyway. If I just look at that again, you imagine that any rain falling here, it's only really going to hit the edge of the balcony anyway. If it's wind blown, you might get a little bit of rain in, but generally, I think they're relying on the fact that by the time you get up to the window, you've probably not got any rain getting onto it. Right. So what they've done, the paving slabs are horizontal. And the great thing about using paving slabs on a balcony like this is that you can have the paving slabs can be horizontal, and the substrate can be on a fall to get rid of the rain, and then the paving slabs simply sit in some adjustable spacers, which is just a product. And these you could screw these to adjust the height, so you can get everything nice and level, and rain can drop through the gaps down the sides of all the paving slabs. So any rain will come through, it will hit that waterproof layer, and it will simply drain away. And there is a sort of gutter, a hidden gutter on the edge of the balcony. Okay. Then we've got let's just draw the glass. So the top of the paving slabs is our datum. That's where we want everything to be flush with. So if we draw the glass again, and like this. That sits on a back box. It's part of the system, and looks like there's a steel angle here. There's another box under here. So I guess this guess this steel angle here is holding that glazing in place here. Then we've got there, got that there. I mean, it's not on my detail. When I gave this lecture a few weeks ago, what I suggested I would have done is probably, even if it's just a sort of self-adhesive EPDM, but I think I would have put some sort of mechanism here, probably, well, either glazed into the glazing system or just face fixed, but just so that when somebody's coming along to wash these windows, you've not got water finding its way into the cavity here. There's not, I mean, the detail I've got, there's nothing shown, but I would have thought there'd be something. Okay, so that's the detail there. There's a paving, there's probably half a pedestal support here. You probably just cut that off, or you might. What you can do actually is put the support back slightly. That's probably better. Get rid of that one. Okay. Then in the gap here, it's just stuffed with insulation. Okay. I'm just putting a grey line on there just to make that concrete a bit clearer. Okay. So, almost there. And then what they've done on the inside, which is pretty simple actually, is they've got a screed finish. So the floor finish in the building is just a screed. You know, that grey, giving that sort of grey appearance, which is, you know, if you can get good quality screed, it's robust. It's not very soft. You might want to put some rugs down if you were, you know, if you're going to sit on it. So we've got that. That sits on a rigid insulation board, like that. And if you were having underfloor heating, which I don't think they've got here, it looks like they've got an air system. But if you were, you would embed that underfloor heating in that screed layer in here. So they have like proprietary plastic clips that they can clip to the insulation, hold those pipes in place. You lay the plastic pipes down, pour the screed over the top, and that's your underfloor heating done. What you should never do is put your underfloor heating in your structural slab. But we did have a project in practice once where we did it. Luckily, it wasn't our decision. The contractor went ahead and did it. So imagine you've got underfloor heating pipes in your structural concrete, and then what happened is while they were building the building, those pipes got full of water. In winter, that water froze, and all of those concrete slabs exploded. So the entire, well, not entire, but most of the concrete slabs had to be cut out and rebuilt. It cost the contractor millions and millions to put right. But luckily, we had a piece of paper that said, this was when I was at BDP, that said, you know, under no circumstances would BDP recommend you put underfloor heating pipes in your concrete. So we were fine, but yeah, they messed up. But yeah, anyway, that's where you put your underfloor heating pipes. Okay, so I think we're pretty much done. There's a little bit of, looks like there's a little bit of maybe just a mastic sealant in that gap with, hard to tell, but probably just a little bit of rigid foam stuffed in there. This gap on the outside, it looks like it's just open. I'm not sure. I probably would put a little bit of sealant in there, because otherwise you could drop your dinner money down that gap, drop your crisp packets. Not very good. Yeah, so that's the, zoom out a bit there. Yeah, that's the principle. So it's achieving this sort of flush effect on the underside, flush on the top. Nothing to sort of cast a shadow. I think that's what's important, that when the light comes through, if you have a frame here, you'll cast a shadow on your soffit, you cast a shadow on the floor, and I guess they wanted this sort of very pure aesthetic. Now, one of the questions that was raised when I gave this to Y5 was about the cold bridging, because obviously we've still got, although we've got this insulation in the gap here, we've still got a steel beam coming all the way through. Now, a few thoughts on that. One is they may well have done some computer modeling to demonstrate that by the time the heat has come all the way through that steel beam, all the way through that concrete, that probably the amount of heat loss is probably quite minimal. I don't know if they did the calculations or not, but I imagine the Swiss standards are pretty high, so maybe they did. The other thing is you've got good ventilation in a school, so you're not really concerned about getting condensation under here, so that's not really the problem. Now the sort of alternative here, what you maybe could have done is if you'd recessed the concrete here, so if you cast a recess in, what you can do with a cold bridge, as long as you insulate for a reasonable depth into the building, then normally you find you've minimized the heat loss. So, what they could have done potentially here, I suppose, is to insulate here, like that, and maybe put a little precast concrete filler piece in here to sort of maintain the aesthetic, but just to insulate a little bit. But as I say, they maybe did some calculations, some simulation, and found that it was not an issue. Okay, but the fifth years were a bit worried about that. Any yeah.
Is the glass cut to form the concrete, or is it
No, it's not. What happens is the glass is rectangular at the top. So if you imagine what I've drawn here is if I draw the section the other way, imagine that's the section in the other direction, and the section that I'm drawing was through this high point. So imagine I've drawn that moment at the high point of the profile. At the low point here, what happens is, do it in blue, that concrete does that. They don't have the blinds. I don't think they have the blinds when it's profiled. So,
Does that make it difficult to get the glass
yeah, yeah. I don't know, to be honest, whether they've done something fancy at the bottom. Ah, yeah, they have. Yeah, good question. Yeah, I'll draw it in a second. But so at the top, that's what you get. Okay, so the glass disappears, and at the bottom, what they've done, I'll just draw this really quickly. Glass coming down like that. So you've got similar kind of detail on the inside, and what they've done on the outside is they've put a drainage channel in here, which I guess you would do as a slot drain. So this is a precast concrete slot drain, which I'm drawing really badly. Something like that. This has a little stainless steel plate on it, so all you see from above is a 10mm little slot. These are great. Put these around your building. They're at Jessup. If you go to the front door of Jessup West, they're all over it. Okay, but you don't need the point is you don't need a big grill. You don't need a big sort of obvious drainage channel. You just have these little slot drains. So I'm assuming what they've done here is, I've drawn it slightly wrong. That's the inside. They then have a paving slab over the top of that, like that. So presumably, to get that glass out, they could take that paving slab off, take that drainage channel out, and then maneuver it out. They'd have enough space to do that. Awkward. I'm sure they've put toughened glass of the highest quality. So you probably could throw bricks at it and it won't break. But yeah, that would be the only way. Yeah, that would be the only way. You'd have to take that drainage channel out. Yeah. Any more comments or questions?
How come they've decided to put the blind on the exterior?
Well, it might be in terms of heat gain. If you.
Got such a large balcony.
I know. I mean, it is a very common solution in Switzerland. The external roller blinds is common. Computer controlled, electronically controlled, is completely commonplace. It does have the benefit that you do keep the heat out, and as you say, there's such a big balcony. But I suppose if you imagine on on the east and the west facade, you've got the building up to the right temperature, the sun starts coming in at a low angle, heating it up. If you block it on the outside, then, blocking it on the inside, it's too late, the heat's in.
I guess it stops kids
Stop kids playing with them, yeah. I don't know enough about that, whether it's computer controlled. You would imagine this building would all be BMS controlled, building management system controlled, and as soon as they sense the temperatures getting too high or the radiation from the sun, then don't know. But certainly in Switzerland, everywhere has external blinds. They do work very well. And I guess because they're so commonplace, they're not so expensive, and they're not so costly to maintain. The trouble in the UK is whenever you propose them, because they're quite rare, they just cost a lot of money. Any other comments or questions? No? Okay. Who likes this building? 50, I didn't like it. Yeah, dead right. Dead right. Yeah. It looks like a factory or an art gallery. But when I was there, it was full of furniture, and I think it's a junior school, and it looked lovely with all, they put rugs all over the floor, and they put
comfy sofas, and really occupied it, and it did look great. But the pictures, yeah, you think you wouldn't want to send your kids there. Yeah. Yeah. Okay, thanks everyone.